chapter 5 is actually the beginning of the second half of calculus, you could say. The first half of Calc 1 is all about derivatives and what they mean and what they can help us do. We've actually accomplished quite a bit with derivatives. Section 2 of Calc 1 would be called integral calculus, where we consider what it might mean to look at the antiderivatives of a function. Okay? But I don't want to get too ahead of myself on that. So what I'm going to do is just try to convince you that it is very important to think about the area under a curve. Okay? So let's just play around for a minute. Let's say that you have a function, right, like this, any function, and for now let's just keep it all above the x-axis. And so far we have looked at the y-coordinates of points, right? Any Algebra 1 student or Algebra 2 student can find the y-coordinates of a point, just plugging in the x, right? And then we've also, as Calc students, we've discussed slopes of the curve. And we've studied concavity of the curve, right? So we've studied f prime, which is slope, and f double prime, which is concavity. And we said that the triple derivative, the third derivative, really doesn't mean much to us. Like, we don't really know what it means. It's like the curve of the, it's like the slope of the concavity or something. But it's not that meaningful to us geometrically. But there is another property of graphs that we have never looked at, and that is the area underneath a curve. In fact, we haven't talked about area at all this year. So what we're talking about is perhaps what might this represent right here. Okay, so the big question of the day is this. I'm going to type the big question of the day. What is the geometric, or excuse me, what is the practical interpretation of the geometric quantity called area? Specifically area under a curve. So what is the meaning of the area between a function's graph and the x-axis? Okay? What is the meaning? That's our big question of the day. And it's something we can actually easily investigate from a common situation we've been dealing with our whole lives. So here is an old fact that we could revisit right now. You guys probably recognize this. Rate times time equals distance, right? Rate times time equals distance. This is just an old 7th grade formula. It's really only true if your rate is constant. If something is moving at a constant rate. Okay? For now, let's just assume that rate is positive. Okay, so it's like a speed only. We're not going to do like velocity right now. Okay, so let's just imagine, I'll write a brief sentence here. A car drives at 50 miles per hour for 4 hours. So let's go ahead and graph what that would look like. So here is midnight, let's say. And then we have 1 a.m., 2 a.m., 3 a.m., 4 a.m., 5 a.m., 6 a.m., 7 a.m. Okay? And so this is like time. And let's say the y-axis represents the speed. Speed, rate, velocity. For my purposes right now, just think of them all as the same thing, okay? So let's go, let's do 10, 20, 30, 40, 50. Okay, so what's going on is, let's say a person has to drive a big truck at night, and let's say that for trucks, the speed limit is, let's say, 50. And so he drives from the hour 3 a.m. to the hour 7 a.m. That's 4 hours of driving at a constant speed, right? So he's driving along, and the speed never changes. He's got his cruise control on or whatever. I don't know if those big trucks have cruise control, but let's just say they do. And he's cruising along 50 miles an hour. He never changes direction, just cruising along. We already know that he travels 200 miles. I mean, it's obvious. If you travel, 50 miles per hour for 4 hours, you're going to travel 200 miles. That's obvious. But my question is, where does that show up geometrically in this picture? Where is the 200 in this picture? Do you see a 200 in this picture? We know that 50 times 4 gives us distance. Even the units alone give it away, right? 50 miles per hour times 4 hours. The hours cancels, we get 200 miles. But where is the 200 miles in the picture? It's area, right? It's the area under this curve. Except I meant to go from 3 to 7. So my points are off a little bit. Okay, so we just went from t equals 3 to t equals 7. That's the 4. And the height of this rectangle is 50 because that's the constant speed. So that 200 shows up here as an area. Interesting. Well, of course it does. Length times width is area. And time times speed is distance. So the distance shows up as an area. But this makes us wonder if maybe the area of other graphs might be meaningful. Does that make sense? Okay. So if you're in physics, this is just old stuff for you. But you have to appreciate, like a long time ago, maybe several hundred years ago, people were thinking about these things, and they're like, I wonder what the area represents, And they're like, wait a minute, if this is like velocity, and this is time, we know for sure that means distance. How can we generalize that, Okay, now let's go on, and let's talk about a decelerating object. So let's say that something at, let's say at 3 a.m., the object is moving at 20 miles per hour, and at 7 a.m., the object is moving at 50 miles per hour. So this object is no longer moving at a constant speed. In fact, let's just assume it's got a constant acceleration. So it's 1, 2, 3, 4, 5, 6, 7. And it goes from velocity 20 at 3 a.m. to velocity 50, but it doesn't reach that top speed until 7 a.m. And let's just assume that it's rising at a constant slope. So this would be called a constant acceleration. This is still velocity, this is still time. Just the units alone, since this is miles per hour and this is hour, we know that multiplying lengths times widths, or x's times y's, should give us distance. It should, just hours times miles per hour should give us distance. And we could assume then that this still means the same thing. This still means distance traveled. Should still mean distance. We're going to find out later it actually represents displacement, not distance. Okay? But for just my purposes right now, I'm going to just stick with distance and speed instead of velocity. We're not going to need directions today. So, distance it is. Now, it's a different shape though, right? It's not a rectangle. So, you're going to have to find the area of this trapezoid. Okay, now some people like to break this down into a triangle and a rectangle, which is perfectly fine. But we are going to very soon need the equation of the area of a trapezoid. And we're going to use it heavily this year. So, let's just go ahead and do it that way, despite maybe how you do it in physics. So, what's going on is we have this trapezoid where this is 4, it really represents 4 hours. And this is 20, really means 20 miles per hour. And this is 50. And let's just tip this trapezoid down like this, so that the 4 is here and the 50 is here and the 20 is here. So I kind of tipped it and collected it, sorry. But basically what I'm trying to do is show you that this is normally how you think of a trapezoid. Actually, no, that's not. You probably normally think of a trapezoid, the two parallel parts here, as top and bottom, right? Okay, so you probably would be more comfortable looking at the trapezoid like this. This is 50, this is 20. Okay, and then like on the SAT, this would be called like base 1, and this is called like base 2, and this is called height. Right? Okay, so do you guys remember the formula for the area of a trapezoid? It actually showed up on your test yesterday. 1/2 h times b1 plus b2. Yeah, right. So the area of a trapezoid is going to be basically h over 2 times the sum of the bases. And don't take this formula for granted. Sometime you need to sit down, okay, and you need to take this picture you need to figure out why the area of the trapezoid is 1/2 times height times base 1 plus base 2. It's not that simple. It's actually pretty complicated going from here to there. But there's a proof, and it's really easy to get the area formula with like b1, b2s in it, and like h is all over the place. But it's really hard to get it down to that clean. So whoever did it worked hard to get that. Okay. I'll give you a hint. If you ever want to try this derivation, think of this as a triangle with a triangle pulled out of it. So you've got a triangle minus this part, which gives you the trapezoid at the bottom. Okay, but in any case, this is the formula that we've taken for granted for so long. And if you have a chance sometime, go prove it. Now, in this problem, in the original problem, remember, the trapezoid is sort of tilted on its side. So the height is resting on the x-axis. The two bases are actually vertical. But that shouldn't matter too much. When we say base 1 and base 2, we mean the two parallel sides. Okay, so just make sure you identify them properly. The height is actually the 4. So you're going to be basically going 4 over 2 times 20 plus 50, which gives you what? 140 miles. Okay, so what's going on in this situation is the distance is only 140 miles driven. And that's because part of the distance was driven at a slow speed, and then he was kind of speeding up. So he's obviously not going to cover a full 200. He's not going a constant of 50 anymore. He's accelerating towards 50, so it's less distance. But again, just because we change the shape of the area under the curve does not change the fact that this represents a distance, obviously. Okay, so you can appreciate then maybe what happened next in history. People wanted to know, well, what happens if we have like a velocity function that looks like this? For example, the tide on the ocean rises and falls. I'm sure the velocity of the water level rising, the dh dt, is not exactly linear. It's based upon the rotation of the Earth and the Moon, the tugging of the Moon and all that, relative positions of the Earth and the Moon. It's probably more of a sine wave than anything. You know what I'm saying? Even if just the position of the water is sinusoidal, the velocity function, which is the derivative of that, would be cosinusoidal. So the velocity functions in real life are not always straight lines, is what I'm saying. Okay, and if that happens to us, we still then believe that this is an important quantity, and we still believe it's distance, but what, we can't find it now because it's too complicated to find the area under here? Well, listen, if this represents distance still, we have to learn how to find areas like those. It's too important not to learn how to find areas like these. You see? So all through high school, you've never once found the area underneath a sine wave, for example, or underneath a parabola. Why? Why have your teachers been avoiding that for so long? It's because we don't have the tools. Frankly, we don't have the tools to find that area, even though it's as important as finding how far something travels. So you can appreciate mathematicians would not settle for this. They're like, wait a minute, that's the distance the object traveled. You better believe I'm going to find a way to find that area. If that is so important, why would it not be important? So, since nature's not straight, we got to figure out how to do it. It turns out we can find the area under any function, most functions, pretty easily. Okay? And it all comes from the antiderivative, which should really kind of blow your mind. Okay? It should put your brain in a knot. That anti-deriving a function will help you calculate the area under its curve. Like, that is more than just trivial knowledge. It took centuries, or at least a long time, for mathematicians to ever realize that. And we're not even show you how they would estimate areas like these. Because you can do it through calculus, but a computer cannot. Most computers do it by approximating, and that's what the ancients did. And so we're going to do it by approximating. We're going to try to find the area under a parabola today using rectangles. Okay? Later on, I'll show you how to use an antiderivative to accomplish it and get an exact answer. Okay. All right, now, my goal today is to teach you three things. Rectangular approximation method from the right, left, and midpoint perspective. And I want to show you that they're not that accurate. And this is how it works. So if you had Mr. Lynch last year, you've already seen this. If you had me, you have not seen this. So it's half of you is new, half of you is not new. Okay. So I'm just going to pick my favorite function. This is the graph f of x equals 4x minus x squared. And we're going to basically estimate using 4 rectangles the area under f of x equals 4x minus x squared on the interval 0 to 4. Okay, so here's our goal. It's actually very simple. This function factors into x times 4 minus x. So your x-intercepts are here and here. It's a downwards opening parabola for crying out loud. We're going to try to estimate this blue area by using 4 rectangles. And we're going to do it 3 different ways. That's what we're trying to do. Okay. So the first one we're going to do is called RRAM. Actually, we'll do LRAM first. Let's do LRAM first. So we'll do LRAM, then we'll do RRAM, and then we'll do MRAM. Let me explain what these are. These are rectangular approximation methods. Rectangular approximation methods. The first one is the left rectangular approximation method. The second one is the right rectangular approximation method, and the last one is called the middle or midpoint rectangular approximation method. So they all have the word RAM in them, rectangular approximation method. Not to be confused with the computer use of the word RAM, which is random access memory. This is rectangular approximation method, and we have left, right, and middle. Okay? So I'm going to teach this by example instead of getting all theoretical about it. Let's just do the problem we've set out to do. So we know what our function is. We'll do LRAM first. Okay, this function basically passes through 0, f of 0, and it goes all the way up and back down, and it hits at 4 f of 4 on the x-axis. And f of 0 and f of 4 both happen to be 0. Okay. Because we're going to use 4 rectangles, we're going to partition this into 4 equal parts. So from x equals 0 to x equals 4, if you're going to break it down into 4 equal parts, you're going to use from 0 to 1, 0 to 2, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So basically just draw a line down the middle, and now you have 2 halves, and then split each half in half, like that. So by drawing 3 lines, we've made 4 partitions. We have 4 pieces. Okay? So we've broken this down from 0 to 4, we've broken it down into 4 equal pieces. The first piece runs from x equals 0 to x equals 1. The second one goes from x equals 1 to x equals 2. And then from x equals 3 to x equals 4. Or x equals 2 to x equals 3. And then x equals 3 to x equals 4. So it looks like that. That's 4 partitions. And now we're going to draw what's called left rectangles. Okay, so this is the tricky part. When you draw left rectangles, you have to look at both of these points on the curve. So let's do our first one from 0 to 1. You pick the first point, the left point, and you draw a line straight across the page. This represents the top of your first rectangle. So because I'm doing an LRAM, I choose the left point, and I draw straight across, and that represents my first rectangle. When I go from x equals 1 to x equals 2, I choose the left point, which is x equals 1 point, and I go straight across. When I go from x equals 2 to x equals 3, I'm looking at these two dots, the vertex in this next one, and I pick the one on the left, and I go straight across. And lastly, when I go from 3 to 4, I start at x equals 3 and go straight across. These are the tops of the 4 rectangles, and they are connected to, their left endpoint is connected to the curve. The right endpoint is just kind of floating. But now you can construct the rest of your rectangles. So draw your altitudes in here. These are called the left rectangles, or the left-hand rectangles. The reason they're called left-hand rectangles is, again, their top left point is stuck to the curve. The top right point of each rectangle is not necessarily on the curve. Okay? So what I'm saying is these purple points are not necessarily on the curve. Okay? We're going to find the area of these 4 rectangles, and we're going to argue that it's not a bad approximation of the area under the parabola. Okay? Okay, now, this first point is 0 f of 0. Let me switch colors. I'll just use a highlighter real quick. So this point is 0 f of 0, or you could say 0, 0. Right? Okay, so that's that point. The second point on this graph, this second green one up here, is the point 1f of 1, which turns out to be the point 1, 3, but I don't really care right now, because I want to keep things general. So this point is also very important. And then this point here is 2f of 2, and this is the point 3f of 3 right here. And we already labeled the last point, 4f of 4. So why am I labeling these? I'm labeling these because these are also, the y-coordinates of these points represent the heights of our 4 rectangles. The y-coordinates of these points represent the heights of the rectangles. Right? For example, the third rectangle has a height f of 2 because it's connected to the curve. So however high this point is also how high the rectangle is. See? Okay, so the area of the first rectangle is obviously just length times width. Or you could say base times height. It's a rectangle. I would say its width is 1. You agree? Okay. So the width is 1, but the height is f of 0. So the length, we'll just use base and height instead of length and width. So we'll say the base is 1, but the height is f of 0. The second rectangle also has a base of 1, but it has a height of f of 1. So the second rectangle has base 1 also, but it has a height equal to f of 1. And the third point, you can see the pattern here. The third rectangle has a base of 1, but it has a height f of 2, you see. And the last rectangle, the fourth rectangle, has a base of 1 and a height f of 3. So suddenly the function becomes very important, because the function 4x minus x squared is how we're going to find f of 0, f of 1, f of 2, and f of 3. So we'll use the function to find the heights of the rectangles. And the total area is going to be like this. Base 1 times height 1 plus base 2 times height 2 plus base 3 times height 3 plus base 4 times height 4, you see. and all the bases just happen to be 1. So I'll just put BH1 plus BH2 plus BH3 plus BH4 because all my bases happen to be the same, which is usually how I design these problems. I try not to use different bases if I can help it. In fact, I'll just factor out the B. So I have B times the sum of the H's which is, since B is 1 for this problem, we have f of 0 plus f of 1 plus f of 2 plus f of 3. This is the LRAM that we want. Okay, now it's time to find f of 0, f of 1, f of 2, and f of 3. Okay, so here's your function. 4x minus x squared. So what is f of 0? It's 4 times 0 minus 0 squared. What's f of 1? 4 times 1 minus 1 squared. What's f of 2? 4 times 2 minus 2 squared. What's f of 3? 4 times 3 minus 3 squared. In other words, we have 1 times 0 plus 3 plus 4 plus 3, which is 10. Finally, we got something we can, like a number we can talk about. What is the 10? What does it represent? The total area of the 4 what? Rectangles. Is it a good approximation of the area under that parabolic arch? Probably not real great. But it turns out that the area under that parabolic arch is exactly 10 and 2/3. So we're actually not that far off. Okay? You might have guessed that this would have given us an area a little too small. There's a lot of space under this parabola that we never captured. We never got this space, for example. We never got this space. And we got a little bit of extra space, like we've got this extra piece and this extra piece. But these pieces are concave down, so we actually gained extra area less than we lost area over here. So this little triangular archy looking thing and this one have a little bit more area than these two that we have here. Okay, so what is my purpose on this problem? I just want you to see how to draw an LRAM rectangle, and I want you to see that it does not give us the right answer. In fact, it actually gave us an answer that's a little too small. Now we're going to draw the RRAM version of the same. We'll speed it up a little, okay, because you don't need to see every little detail. For RRAM, you probably guessed that we're still going to draw the 4 partitions, the 4 equal partitions by drawing 3 lines. So we're going from 0 to 1 to 2 to 3 to 4. And this is going to provide us with 4 partitions, 4 rectangles, but we want the right endpoint of each interval to be connected to the top of the rectangle. So here's how I do it. Okay? I start at 4, because we're doing right rectangles, so I actually start on the right. So I look at these 2 dots over here, between 3 and 4, and I choose the one on the right, and I draw my rectangle straight over to the left. Notice that this rectangle, as we saw in the last example, has no area at all. It has no height, but we draw it anyway. Okay, so there it is. Then we come over here and we draw between 3 and 2, we start at 3 and draw a line backwards. So I'm drawing to the left here. Then between 2 and 1, we start at 2 and draw a line out to the left. Obviously stop when you get to x equals 1. And lastly, for 0 and 1, we'll start at 1 and draw a line backwards. So I'm drawing arrows on here because I want you to see which direction I was sketching. So I start on the right and I sweep backwards. And now you can see these are the tops of your rectangles. So your rectangles look something like this. So it turns out that LRAM and RRAM are going to give us the exact same results, but that is typically not the case. It's true on this problem. Let's just go ahead and write down the area of the 4 rectangles. So here we have B1, H1. That's the area of the first one. This one's going to be B2, H2, B3, H3, and B4, H4. These are like your 4 areas. We'll then add these all together to get our RAM approximation. Okay? That's our plan. Move that down. Looks like my axis came with. Oh well. Relabel those. 0, 1, 2. Okay. So this is going to be my RAM approximation. Notice I'm still keeping it, I'm kind of doing this by design. I'm trying to keep all the bases the same. Some people don't like to do that. Some people like to have different bases. But for me, I like to have the same base. That way B1, B2, B3, B4 all the same, and I can factor it out. So let's just make them all the same. They're all 1, and we'll just factor that out. So we'll factor out the B. Okay, so like we saw last time, this is just H1 plus H2 plus H3 plus H4. And this time, you'll notice that the height of the first rectangle is no longer f of 0. The height is f of 1. So the height of the function at 1, also known as f of 1, f of 1 is the height of our first rectangle this time. Last time it was f of 0. So how tall is this thing? It's f of 1 tall. That's how tall it is. Okay. So this is going to look a little different this time. It's going to go like this. Watch. F of 1 plus f of 2 plus f of 3 plus f of 4. Last time, we did not have the f of 4. It went 0, 1, 2, 3. This time it goes 1, 2, 3, 4. And you can use your function to get your f of 1, 2, 3, 4. Basically, they come out to be 3, 4, 3, 0. So this is just 1 on the outside because I kept all my bases the same length. Each base is 1. D equals 1. Okay. And this comes out to 3, 4, 3, 0. Final answer, 10. 10. Okay, so you can kind of tell from the symmetry alone that this would give you the exact same 4 rectangles, just kind of shifted over. So we call this our RAM because the top rightmost point of each rectangle is physically connected to the curve. Which brings us to our last drawing, MRAM. I know it's been a long week. Some of you guys try to stay awake. Okay, so here's our graph, our third case. 0 and 4 again. Okay, so you're still going to partition using 3 lines. So right in the middle, so at 2. And then between 0 and 2, you've got 1. And between 2 and 4, you've got 3. And your rectangles still fit in these exact same domains, but this time we're not interested in either of these green points. We're interested in the halfway point. So what is halfway between 0 and 1? 0.5. So go to 0.5 and go up, 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 up until you hit the curve. From there, go left and right. So sketch back and forth like that. This is our first rectangle. I'll shade it this time. So my first rectangle looks like that. Notice that the height of this rectangle is actually connected to the point halfway between 0 and 1. Okay? You can already see that this is going to be a much better method because the true area that we seek to find is what I'm shading in green right here. This is what we want to find. It doesn't look green, does it? actually, let me back up just a little bit. I just want to show you what we're trying to find. We're trying to find this blue area. Okay? That's what we're trying to do. Right? But we're going to have to settle for just the rectangular part of it. You see? But they're not that different anyway, because if you look at the blue area, right? Our rectangle doesn't include this little part of blue. Right? Our rectangle's right here. This is our rectangle. Our rectangle does not include this part above. We didn't get that area. But we got that area over there. That little sliver. And you have to admit, these two little triangular looking regions were pretty much the same area. Right? See that? Okay. So this is going to give us a much better approximation than LRAM or RRAM would. Now let's go halfway between 1 and 2. So what's halfway between 1 and 2? 1.5. So start at 1.5 on the x-axis, kind of sketch upward. When you hit the when you hit the curve, cut back and forth to form the top of your second rectangle. Erase that shading real quick. So we went from 1 to 2. Went halfway, and then we cut back and forth. There's your second rectangle. So there are two rectangles. Notice that the top of this rectangle does not connect to either of the green points. It connects to the point between the green points. So the top of the curve actually does not pass through either corner of the box. It passes through the center of the top of the box. Okay? All right. Next we would go to 2.5. You don't have to draw this dashed line. You're not really supposed to. So. And you'll notice that the way I'm designing this, the rectangle that I drew from x equals 1 to 2 and the rectangles I drew from x equals 2 to 3 are exactly the same size. So the last two rectangles we drew are the same. And then the last thing is to go to 3.5. So halfway between 3 and 4. So go to 3.5, find the curve by going straight up, sketch your last rectangle. So I'm going slow because for some of you this is the very first time you've ever drawn an MRAM situation, and it's a little harder than drawing the LRAM and the RRAM. So the parabola passes through the midpoints of the tops of each box. You see? All right, so right here in blue, that's a midpoint, that's a midpoint, that's a midpoint, that's a midpoint. Okay, these points are very important. This is the point 1/2, comma, f of a half. So it's 0.5, f of 0.5, you could say. This next point is the point 3/2, f of 3/2. This is the point 5/2, f of 5/2. And this is the point 7/2, f of 7/2. And those y coordinates are our box's heights. See? So we're going to do the same thing we did before. Area is always the sum of the areas of the rectangles. This is now called MRAM. And it's base 1 times height 1 plus base 2 times height 2 plus base 3 times height 3 plus base 4 times height 4. But all the bases are the same. So I'm going to factor that out if you don't mind. And I've got h1 plus h2 plus h3 plus h4. And those heights are f of a half plus f of 3/2 plus f of 5/2 plus f of 7/2. Since each base is 1, And f of half would be 4 times a half minus half squared. And f of 3 halves would be 4 times 3 halves minus 3 halves squared. And so on. Minus 5 halves squared. And one more. 4 times 7 halves minus 7 halves squared. All that remains is that we calculate what this comes out to. So 2 minus 1/4, you can think of that as 1.75, so I think decimals is going to make more sense in the end here. Then we have 6 minus 2.25, which is 3.75. And just from the symmetry alone, we already saw that the last two rectangles are the same areas as the first two rectangles. They're the same rectangles. So this is just going to go 3.75 again and 1.75 again. You can check my work later if you want. So these two combine to make 7.5, and these two combine to make 3.5. So you just basically get 1 times 11. 11. So now, is this the area under the parabola? No, this is not the right area either. Listen, the only way to get the exact area is using calculus. But we know the area is something between 10 and 11 now. And the 11 is actually pretty darn close. You saw geometrically that the area of these purple rectangles isn't that different from the actual area under the graph. We're trying to find this area under the curve. And the MRAM so far has been the best approximation. I mean, look at the wasted areas on the edges. Like here we have a little bit of area we didn't need. We got that in this rectangle. But then look over here. This little bit of extra area that we didn't get kind of canceled out the area we didn't need. You see? So like we needed that, we didn't get it. We got this, we didn't need it. But they're pretty much the same anyway, except they're kind of capped the hypotenuse. It's like, oh, hypotenuse thing is kind of this one's concave down, that one's concave down. So this one's kind of concave with a triangle, that's sort of a convex with a triangle. So they're not exactly the same, but I'll bet this answer is darn close to 11. Now, how could I, if I stick to this rectangular approximation method, how could I increase my accuracy? How could I increase my accuracy? Yes? What do you mean by that? Increase? Yes. If I were to do 6 rectangles, my errors would be less. And it'd be a lot more work. 4 was enough work, don't you think? Probably don't even need LRAM and RRAM, right? They're not very accurate. But if we did an MRAM with like 100 rectangles between here and there, that would be super, super accurate, right? And a computer would have no trouble at all adding up H1 through H99 like that. I mean, it can do it faster than you can say Ritzcraft. Okay? Now, what is the general takeaway? Well, if you're going, watch close, if you're going from A to B, then you're going to want to break it down to into a certain number of sub-intervals or partitions. So that is going to be like the height of each rectangle, right? So imagine a rectangle here. How wide is it really? Well, it's B minus A divided by how many rectangles you chose. So if it's 4 rectangles, then it's B minus A over 4, right? If it's 20 rectangles, it's B minus A split into 20 parts. This is like your height, you see. And that's assuming you keep all your bases, I mean, this is like your base. This is assuming you keep all your bases the same. Okay? Your heights really depend on the function. Those are like your y values in the function. So the heights are just like f of x sub I, where it could be f of x1 or f of x2 or f of x3 or whatever. Okay? Okay, so here is what LRAM, RRAM, and MRAM look like in a more general sense. Okay, so forget the function example. Here we go. LRAM would look like this. You would have a B minus A over N out front, where N is the number of rectangles. okay? And you get to choose that. So b minus a over n. And that's your base of the rectangles, and that factors out. On the inside, you'll have f of 0 plus f of b minus a over n plus f of, let me actually use an a. We'll start at a, not 0. So we'll go from f of a to f of a plus b minus a over n plus f of a plus 2 times b minus a over n. And this is just going to go on and on and on until you get to f of a plus n minus 1. Okay, so it's n minus 1 times b minus a over n. And that's where it would end. So it's going to go from f of a, which could be f of 0, but it's going to go from f of the first point all the way up until you keep on adding on these little rectangular widths until you reach n minus 1 of them. So you're not going to actually reach the end. This is what LRAM looks like as a formula. Okay, you can even put it in sigma form, but we won't. Okay, RRAM looks almost the same. It's b minus a over n times f of a plus b minus a over n plus f of a plus 2 times b minus a over n plus and so on until you get to f of b. So you will actually reach f of b because you include the right endpoint, as you saw in the examples. And MRAM is just ugly. MRAM will look like this. You would have a b minus a over n, and then you have f of a plus half of b minus a, so b minus a over 2n, plus f of a plus 2 times b minus a over 2n, which actually simplifies, but don't. Keep going until you reach f of a plus, and basically it's going to be just, you have n rectangles, here's b, so this is a plus n minus 1 times b minus a over n. All right, so 4. And this is b over here, and you're halfway between them, so you average these together. So it's kind of awkward, but it'd be basically I don't even know. I'd have to write it out. But basically it'd be just before b, halfway between the last a you used and the last b. So I won't write it in right now, but you can see these formulas are pretty ugly. And it all stops when you get to that last rectangle. Okay? So this is why we'd probably want a calculator to do our work for us, or a computer. So I went ahead and when you guys were just sitting down today, I went online and I just downloaded, well I actually kind of had it downloaded already. I basically just found a program that will do this for me. So I'll show you. It's not working. Come on. I need this. Yeah, go away. Okay, there we go. So the program I downloaded can do LRAM, RRAM, MRAM. And when you select which one you want to do, so let's say you want to do LRAM, you got to type in a function. So why don't we just do 4x minus x squared? We already did this problem. Let's see if we did it right. Enter. Left bound. Let's go from 0 to right bound 4. And number of rectangles. We did 4 rectangles. You remember the answer was 10? Let's see if we're right about it. Yes. LRAM area is 10. Let's hit graph 2 to draw. Hit graph to draw. Okay. Hit graph. So it's sketching it now. It's going to draw us a picture of the scenario. That's the area we were approximating. I think it's going to try to draw rectangles for us too. No, it didn't. That was really lame. Okay, they're supposed to draw me some rectangles, my little LRAM rectangles. Okay, you can run program again. This time let's see. Let's look at MRAM. Same function. So 4x minus x squared. Oops, I typed 2x. Clear? How do you quit? Quit. Done. Okay, program. MRAM. Okay, 4x minus x squared. Left bound 0, right bound 4. Let's do 100 rectangles, and we definitely won't ask it to draw. We got 11 when we did it by hand using 4 rectangles, but the calculator, I guess I could have said risk factor 3 or 4 times, but it took a minute, but it figured it out. It took basically 100 rectangles, and it did basically what we were putting out here, and it just ran through a program loop, and it did its job, and now we've got 10.662. You get the feeling, 10.6672, you get the feeling that it's around 10 and 2/3. So later we'll have to show that it is exactly 10 and 2/3 using calculus. Okay, this is a handy little formula. A handy little program. It's free online. I think I got it off of ticalc.org. Okay, ticalc.org. And you just have to connect your calculator to your computer and dump it in. Or if your friend has this program, just get one of these little transfer cables, connect your 2 calculators, and do a link transfer. I can show you how later if you want. This little cable will do it. Okay? All right, let me stop my recording.